Good morning, teachers and students. Hope you're having a great day today. Teachers, please make sure all students in your classes do have a desk shield this morning. Any extra desk shields that you have after you've distributed this morning, please send those down to the front office and we will keep them down here for anyone who may need one. Also today for our lunch menu, chicken nuggets, mixed vegetables, mashed potatoes with gravy, roll, and assorted fruit. Students, if you think you want a lunch, please raise your hand for your teacher this morning so we can get an accurate lunch count. Teachers, please put that in before 9. We ran short yesterday and we want to make sure we have plenty of food, so please make sure you get those numbers in as soon as possible. Thank you.
Okay, who all wants their lunch today? All right, yeah, raise your hand. Okay. 1, 2, 3, 4, 5. Anybody else? All right, so the first thing we're going to talk about is determinants. And then you use determinant to help you find an inverse of a matrix. One of the reasons that we look at inverses of matrices is because you cannot, what's the only 3 operations we've done with matrices so far? Good, multiplying, adding, and subtracting. You cannot divide matrices, so you have to know how to find an inverse, because if you technically are supposed to divide in the problem, then you actually use multiplying by the inverse to solve or undo a certain operation. All right, every square matrix has a determinant. So that's also important that you know that. If I have a 3x2, that does not have a determinant. Only square matrices have a determinant. What makes a matrix square? It has the same, what'd you say? Good, your dimensions are the same, like it has the same number of rows and columns. So like a 2x2, 3x3, so on. We're gonna look at a 2x2, 3x3. 2x2, of course, is the easiest. And I mean, both methods are the same, are similar. All right, look, for a 2x2, let's say we have matrix A. With these elements, you will see determinant either denoted like this, or you may see just vertical bars and not brackets. Okay, how you find the determinant of a 2x2 and for a 3x3 as well, you start at the top left and you are going to multiply to the bottom right. So pretty much you're just cross multiplying for a 2x2. This product right here, you subtract the product you get when you multiply in the other direction. So what's the determinant of A? Okay, for a 3x3, there's 2 methods. We looked at last year in Algebra 2 Trig, you looked at the arrow method and you also looked at expanding by minors. Okay, for the arrow method, your first step is to write the first two columns to the right. Write the first two column numbers out to the right. Okay, in a similar manner of a 2 by 2, you start at the top left and you multiply diagonally all the way through 3 times till you reach that bottom right number. And if this is the way I would do it, or the way I do it, I just go ahead and write the product of each like underneath. Can anybody tell me what we will do with those values? Okay, then you have to add all of those up. So I get negative 52. And then I have to go the other direction as well. So similar to a 2 by 2, I start at the bottom left, multiply all the way through 3 times to get to the top right number. You get 30 that way, 0 multiplying all those, and you get positive 42. All right, last but not least, what did we do here with our determinant value, with our products that we multiplied? You subtracted. Which order do you think you subtract these in? Negative 52 minus 72. Always make sure that sum minus this sum. Okay, any questions about 2 by 2 determinant, 3 by 3? Do y'all remember that last year? I love determinants. Like, give me that stuff all day long. Other than, do y'all remember trig identities last year at the end of the year? Or, well, I guess it should have been at the end. That's why I know y'all are saying, yeah. Okay, now that you know how to do determinant, we're going to look at a couple of problems that involve determinant and maybe working backwards to solve for missing elements. You have on your test Friday, you have two 2 by 2 determinants to find, and you have one 3 by 3. And then you also have a problem just like this. Solve for x. Hey.
Can I see Eric?
Yes, ma'am. Who did you say?
He's supposed to be your student aide.
Oh, yeah, he was on here. That's what, yeah, he's on here. I don't think, no, I don't see him. That's why I was like, they just kind of, he's new, I don't really know. And that's why I was like, hey, yes. Okay, they give you determinant value, find X. Tell me how you would set this up. Good, negative 5X minus negative 6 equals 22. And then just go through and solve it from there. This turns into positive 6, so subtract 6. And X equals negative 16 fifths. Okay, I believe most of you saw this last year in Algebra 2 trig as well. You can actually use determinants to help you find the area of a triangle that's graphed in the coordinate plane. As long as you know it's 3 vertices in ordered pair form. Okay, so let's say I've got a triangle graphed in the coordinate system. You know that its coordinates or its vertices are 2, 5, 8, 7, and 5, 10, and find the area. First of all, you know the area can never be what? Good. Area can never be negative. That's the only reason this positive and negative are out front, because sometimes when we plug in these X and Y's, where you see X1, Y1, so on, and we do the 3 by 3 determinant, we'll end up with a negative determinant. But if you do that, you've got a positive or negative out there in front to negate that and make it positive. So just always remember, when you're doing these type of problems, if you get a negative determinant, just simply make it positive. All right. Remember that in the area of a triangle formula, you have 1/2 base times height. So it's kind of neat how that plays into the determinant method. All you're going to do, you take your vertices, just make sure that you list all your X coordinates, 2, 8, 5, in this first column, Y coordinates in the second. Ones are always filled in down the right column, always. That's in your formula. Make sure, of course, if you say that 2, 5 is going to be your second coordinate, that you list 2 with 5. That's the only mistake I see people make on this. Okay, so all you're going to do is just fill in. You're going to do your 3 by 3 determinant first, and then you're going to take half of it. So taking half is the very last thing. And then what is down the right column? 1. Okay, so we've got to determine the 3 by 3. you write your first two columns out to the right. And multiply all the way through 3 times from starting at top left to bottom right. And then multiply in the other direction. And then subtract and take half. So you'll have half of 119 minus 95. So what is your area? You should get 12. 12 units squared. Hey, you might have a question about that. Okay, we're gonna look at inverses and then move on to the next thing that uses inverses. Let's say you got matrix A with these elements, A, B, C, and D. You have to figure out your determinant first, because that tells you whether or not your matrix is gonna have an inverse. If the determinant of A equals 0, it has no inverse. So if determinant is 0, no inverse. If your determinant is anything other than 0, then it does have an inverse. So determinant equals 0, no inverse. Determinant not equal to 0, inverse. If it has an inverse, you use that determinant value in your formula. So A inverse equals 1 over the determinant. So in a lot of inverses, you're going to have fractions. This actually creates a fraction. You have to multiply that to all the elements you get in this new matrix. You're going to switch places with A and D. And B and C change signs. B and C change signs. Switch, change, switch, change. After you distribute this fraction to those new elements, you will have your inverse matrix. So you've got matrix B is -5, -1. And they ask you to find B inverse. You have to first determine what? Good. Figure out the determinant and see if it has an inverse. What will B's determinant, or what is B's determinant? Multiply this way, subtract what you get when you multiply that way. So -17. So does it have an inverse? Yes. So B inverse equals 1 over that value times the elements you get. What are you doing with -5 and 3? Good, you're swapping places with them. What are you doing with -1 and -2? Change their sign. So they both become positive. Last but not least, distribute the -1/17. All right, next thing we're going to look at, and we're getting close to being done, is writing matrix equations as systems and vice versa. So back in 8.1, and what you're going to have to do on your test as well is write a system, like given to you in XYZ or XY. You're going to have to put that in an augmented matrix form. In 8.4 and 8.5, what they're going to give you, they may either give you the equations, or they may give you something like this. Okay, they give you your system in matrix equation form. And what all this means, this represents your variable matrix. Of course, that's what we're trying to find is X and Y. This is called a coefficient matrix. These values across represent the values in front of X and Y. So this equation, tell me what this equation would represent. Okay, so I know that like numbers, X is in the first part of this column and Y of course is in the second row of that column. If you go across, this is how you would write this as a system. So you would have 2x minus 2y equals -2. This is your constant matrix. What would the next equation be? Like using that second row. 5x plus 3y equals +2. People usually want to associate 5 and 3 as being both your y coefficients, but if you find the inverse of this matrix, multiply it to this one, the numbers left in the top and bottom will be your x and y. So it doesn't necessarily mean that every number is associated with y. So be careful about that. Okay, so you have one problem on your test that gives you this and asks you to write the system of equations from it. So just go across. Even if you have 3 rows, 3 variables, you would say 2x is -2y. What do you have to be careful about? What if something's missing, you have to fill in with what? 0. All right, let's reverse that. Okay, they want you to put this in a matrix equation, which means you're going to have a coefficient matrix, variable matrix, and that's set equal to a constant matrix. Okay, tell me what's your variable matrix going to consist of? X, Y, Z. What are all the coefficients across here? Okay, 1, -1, 1. Second row. 0, 2, -1. 3, 2, 0. Once again, always make sure that if you list the X coefficients down this first row, you do that all the way through and so on. Okay, what is your constant matrix? 0, 2, 9. So that's how you take a system and write it as a matrix equation. What you did in, I'll show you really quick the difference. That's the matrix equation form. If I were to write that in an augmented matrix, and you'll have to do this, remember we would have 1, -1, 1, 0, 2, -1. And then we had that vertical bar. So that's an augmented, and that was from 8.1. You've got a problem in your 8.4, 8.5 assignment. I gave you a review problem from everything you'll see on the test in this assignment as well. So I did kind of give you a small review. I told you I didn't. Okay, in this problem, they give you the matrix equation, and in part A, they ask you to write the system. We already done that in that last part, that first example that I was showing you with this. So just go back to that. In part B, it asks you to solve using inverses. So we're trying, of course, to find X and Y, but we have this matrix multiplied to it. And I know, of course, I can't divide matrices, but what's the same thing as dividing by 5? Good. You can multiply by 1/5, multiply by its inverse. So that's why we went through inverse of matrices. So we're going to find the inverse of this one. We need the inverse. And then you have to make sure that you multiply the inverse before this one. Okay, let's find our determinant. What's your determinant for this 2 by 2? You have 6 minus -10, which becomes what? 16. Okay, since that's not equal to 0, which all of these should have an inverse anyway. So we have 1/16. Tell me, what does this first row of elements become? Good, 3 and +2. What about the second row? Good, -5 and 2. Distribute the 1/16. All right, now that we know our inverse, the last step to find xy, you multiply that inverse matrix times your coefficient matrix. Okay, so of course, multiplying, you take every row in your first, multiply it to every column in your second, and we only have one column. This is what I always do that helps me when multiplying. I'll write this row 3/16 and a blank plus 1/8 blank. I'll write it across however many times I have columns, and I only have one column. And then go back and fill in with the numbers in that column. Don't you guys love all these fractions? This is awesome. Okay, do the same thing with the second row of numbers, -5/16. Okay, I'll go through and multiply, of course, and then I left them to where they would have a common denominator instead of reducing 2/8 to 1/4. And then finally, once we add, we are good to go. Okay, so what is the value of x? X is negative 1/8 and y is 7/8. Okay, does anyone have any questions so far? Yeah. Yeah. Okay, you're going to see a problem just like this, very similar to what we just did. They're going to tell you to write the linear system as a matrix equation. They give you a space for you to fill in your coefficients. They already give you your variable matrix. And of course, you're going to fill in 0 to 9 in your constant matrix. Now, what they do for a 3x3, they go ahead and give you your inverse. So you don't have to find it. So all you have to do is simply fill in your coefficient, fill in your constant. Then you're going to take this inverse matrix and multiply it to what? What would you multiply? What would be out to the right? Good, the 0 to 9. And that's all you would do. And all you would have, and you would just have like negative, you'd have this row multiplied to these three numbers, and you would multiply and add to get x. Do y'all need to see that? Are y'all okay with that? Do y'all want me to show you how you'd multiply that to 0 to 9 and get x, y, z? Sure. Okay, let's do it. No, she's in her big face. She's across the hall. Okay. Okay, so once you multiply your inverse to that constant matrix, you're going to have x, y, z. So take this first row of numbers and say -2 times blank. It's -2 times blank plus 1 blank. And why do you only write it one time across? Yeah, you only have one column. If I had two columns in this matrix, then you would write that one more time, like out to the right. Okay, take your second row, the same thing, 3. And last row. What do you go back and fill in? Tell me what these numbers across will be. Good, 0, 2, 9. And of course, just go through and multiply and then add. You get positive 5 from that first row, negative 3 from the second, and negative 8 from the bottom. So what is the x? 5, good. And y is negative 3, and so on. They ask you to write your solution. They give you a space, write your solution as an ordered triple. So of course, just list it in order: 5, negative 3, negative 8. I think MATLAB asks you to do that sometimes too. Okay, very last thing. I think I may have already told you about this previously. If you multiply two inverses, if you multiply two matrices and you get this result, for a 3 by 3, or you get this type of result for a 2 by 2, and of course, so on. If you have ones along your diagonal from top, left, bottom, right, zeros everywhere else, then that is multiplicative inverses. You have a question, I think in 8.4 and 8.5, that asks you to find the product, and then ask you, are they multiplicative inverses? So this is the answer you get. And of course, 4 by 4, you'd have ones all the way down, zeros everywhere else. You really shouldn't see a 4 by 4 though, as a result. It'll either be a 2 by 2 or a 3 by 3. Okay, does anyone have any questions? All right, work on your 8.4, 8.5 math lab.